Okay, so Clément, let's resume then with the second part of the tutorial of Clément on phase mixing, please.
Okay, so let me just remind you. The last thing I said, or I showed, was this averaging lemma estimate. I just want to make a remark that actually you could have done the same with a B of V here, a vector B of V with, as always, the matrix here. Let's say, well, I don't want to cheat. I would need a little bit more to do the exact same proof. You would need that this matrix is more or less equivalent to identity, bounded above and below. You see something like that. If you would have this, you can observe that the proof would be actually very similar. You would change here, you would have a B of V here, and pretty much everything would behave the same because you would estimate the two regions. They would have a slightly different look in V space because you'd have a B of V, but it would work the same. So I just want, the reason I'm telling you that is because I just want to convince you that it is actually, and I mean, what I'm telling you is well known. I mean, the fact that averaging lemma still are true under this non-degeneracy condition is of course well known. For instance, a colleague was produced, I think, pretty optimal statements about that would be Patrick Girard, but many others have worked on that. So averaging lemma for with the source term still hold with the non-degeneracy condition. And like I said, I'm just saying that to try to convince you that it's again a manifestation of the same underlying dynamical principle. So manifestation of same underlying weak mixing. Right, if you can think that there's enough weak mixing so that some local averages are more regular. That's the way to think about it. Okay, so now let's go into this last estimate. And the funny thing about this estimate is that it was both more or less known, but known in simple cases that were not, I think, let's say, they were not enlightening enough for people to think that they could make precise estimates and use them at the nonlinear level. But phase mixing would be the final and last manifestation of this weak mixing. The less used so far in PD. So these 2 hours mini course is essentially an advertisement for trying to use it so far. I'm going to include some open problems now in at this hour. So we start with the well-known, and that was well-known before the first nonlinear theorems appeared about 10 years ago. Well-known and important outcome, but somehow the outcome itself is not really the core of it. You need a more precise mode by mode estimates to really see how to use it for PD. So let's start with the outcome. Let me state it this way. I'm considering, as always, you can vary with B of V. And I'm going to put my initial data in L2X H1V, and I'm also going to consider a test function var phi in L2X H1V. Okay, then I'm going to state two properties. They are manifestation of the same thing, but they are sort of enlightening in their own right, both of them. That the average of FTXV against var phi of XV, average in X and V, converges with rate T-1 towards the average in X of averages, sorry, the average in V here of averages in X F initial, averages in X var phi. Okay, so that might look a bit mysterious, but what it means, it is just a precise quantitative way of writing a weak convergence of F towards capital F of V. Oh, and of course, I forgot the key information. Obviously, X is in the torus now, and I'm going to take, just for simplicity, a torus with volume normalized to 1. And F of T going to a function of V only. So F is a function of Tx and V, and this is a weak convergence. And it's going to a function of V only as T goes to plus or minus infinity. It happens in this case to be the same. At the nonlinear level, it will not necessarily be the same limits, which is just the partial average in X of the initial data. So it's a way to write this weak convergence. Second point is that if, and of course, nothing is optimal in these statements, it's just an example. Imagine my initial data is L1X W D plus alpha, or I've used alpha before, D plus L 1 in V with L and integers, non-zero. Then, if I define rho of T, so my rho not very different from the F, sorry. Rho T of X, the partial average, I mean, you're used to these notations. And rho infinity would just be the integral in X and V of F initial. Then rho of T minus rho of F infinity, of rho infinity, sorry, is going to 0 with this rate T minus D minus L. Okay, so the first point is maybe more natural when you work on it for a mathematician, but it's not natural at all from a physics viewpoint. The second point is much more natural. The second point is a convergence of the observable, the thing you actually measure physically. You never have access to the microscopical velocities. The distribution of velocities is inaccessible to observation most of the time, but you can measure, for instance, in the plasma, the local spatial density. So this is the observable things that you want a convergence on. A remark is that so far I was not paying too much attention about the domain in X. It could be the torus or RD here, because X is in RD. It means that there is local dispersion. The dispersion mechanisms still function locally, but no global dispersion as before. I'm saying that to emphasize that phase mixing estimates are genuinely not exactly this, they're not the same conceptually as pure dispersion estimates. Like global dispersion would be escape at infinity in X. Instead, you have a certain global dispersion of the velocity frequencies. but that's another story. Here, the energy is sent to the high velocity frequencies. Okay, so let's prove that. Let's Fourier transform, and this time I'm going to Fourier transform x to k. So I'm not using c to remind you that it's a discrete variable now because x is in the torus, and v to eta. And let's use tilde this time for this Fourier transform, since I don't want to confuse it with the previous one, which was in t and x. I don't care about the constant as always. There might be a size of box because I want my box to have volume 1, but I won't pay much attention to this. And we'll have that. And the key point is that now the equation is just the dual of the equation we had before, dt of f tilde minus eta grad, minus k grad eta of f tilde. And the solutions obviously are like that. K eta plus kt. And so now, let's now prove the 2 points. So you remember the first point was discrete convergence. So just define, I'm just going to remove the x average in order to remove the k equals 0 mode. That's all. Which is actually something we do in practice in papers doing nonlinear estimates, and you deal with this. This won't be constant anymore, but you will deal with that separately in the estimates. Okay, so x. So doing that, you get that the Fourier transform in x and v of this g function is exactly the same as the Fourier transform of f, except at the k equals 0 mode, where you actually remove the k equals 0 mode, which is conserved in time. So I can, instead of writing it at ft, I write it at f initial. And let me remind you, it means that g equals 0 at k equals 0. That's what it means, really, to make this formula simpler. And now you just estimate g average in xv against my test function, and I'm just using Plancherel. So there's a sum in k, an integral in eta, but since it is 0 at k equals 0, I can remove the 0 mode. That's what's the whole point. And you have a nice formula in Fourier. And now I'm just going to Cauchy-Schwarz, doing a Cauchy-Schwarz here, but putting some appropriate weights. So that's very simple. By the way, this calculation is almost line by line the same as the core calculation you do for the Quet flow in works on implicit damping. So I'm using the Japanese bracket. So bracket like that just mean 1 plus something squared, square root of everything. I'm going to recall it in a second. So that, and then I have finally my weight, 1/2, and this means 1 plus z square root. Okay, so now I'm using simply that G satisfies the transport equation. So this is just F initial K eta plus KT squared and this weight. And now this weight can be absorbed in the regularity in V, which corresponds to a weight in Fourier. And for the second one, I'm going to add one more weight in eta, because I can assume that my phi is regular in V, and take the sup of the negative of this one and the one in eta. Okay, let me write it. I hope it will become clear when I write it. Okay, what I said is that I add that by force. I remove that one by a sup together with 1 over that one by a sup. So I end up with all of that multiplied by sup in K non-zero and and also sup in eta of eta minus 2, eta plus kt minus 2. And now the basic observation is that that is always less, oh, and I have a 1/2, sorry. And then the basic observation is that this gives you a t minus 1. Okay, it will be a t minus 2, but you have a 1/2. So it's very simple, but I mean, it's the core of everything for this phase mixing estimate. I hope you see it, right? Because either eta is less, so to prove it, if eta is less than kt over 2, then this one gives you this decay. Remember that k is at least 1 because it's not 0 and it's a discrete mode. Or and I'm going to put another color, and if eta is greater than kt over 2, and you still have the k greater than 1, then you're using this one. So you're using this one, right? You drop this one and you use this one to produce the decay. So all in all, you get the decay. I've used a bit of regularity on the test, a bit of regularity on F, which is why in the end it's a weak convergence, because I've used some regularity on the test function as well. And you produce the decay I announced. Where is it? Yes, so you produce this convergence as t minus 1. The limit has been absorbed in my definition of G. Second point. Now we work directly on the spatial density. So rho of tx, I remind you, is the integral in V of f of txv. And rho, let's use hat when there is only one variable. Rho of hat of tk is Fourier of f, Fourier of that in x, but the integral in V can be written as Fourier in V at Fourier frequency 0. And because f satisfies the transport equation in Fourier, this is f initial at k 0 plus kt, so kt, right? I'm just using the formula in Fourier for the transport equation. You do similar thing as before. I'm defining a rho minus its average, its targets. You remember that rho infinity is the average of rho, which is the same as the average initially. So that removes the 0 mode. So I'm going to go slightly faster because the reasoning is very similar. This one is again the Fourier transform minus, and I kill the k equals 0 term. So that produces something that is 0 at k equals 0. And then rho at time t minus rho infinity, L infinity. So remind you, we are in the torus. So I'm looking at L infinity in the torus is less than, so I'm using simply that L infinity of a function is less than L1 of its Fourier transform, or anti-Fourier transform if you want. So less than k in ZD, but the k equals 0 mod is 0, so I remove it. Like that. which is less than, now replaced by this formula. This is less than this. And just observe now that this is equal to the same with additional weight, d plus L divided by the additional weight. Of course, I'm writing something trivial. And I will just put in, okay, let me write one more line to make it very clear. If I put that with the weight d plus L, and on another one, I'm going to put all these terms. So what I'm simply claiming is that this is less than, so how did I call it? This is less than F initial L1. Sorry, there was no sum here, of course. Otherwise, there would be too many sums. So it's a sup. Sorry for that. So if it's a sup, then I go from sup to L1. And here there was Fourier. So sup of the Fourier is less than L1 of the function. We are there. L1 in X of D plus L derivatives in V. Okay, and for the second one, while you just look at it in the eyes and you see that K is never 0, I put enough power so that this is a summable sum. And so you get that this is less than T minus D minus L. And so you deduce the result. That times that is exactly what I was claiming in my second point. So we have a convergence of the density, strong convergence of the density. So summarizing, weak convergence of the whole distribution, strong convergence of the density. But now, after all the discussion we have done before, it should be absolutely no surprise. The phase mixing is weak. It's a weak mixing. It's mixing in a phase space, not a full mixing in space. So it's only local averages that will give you some level of mixing. So you local average in V and you get some strong convergence, but otherwise you just get weak convergence. Okay, so now that we've done an estimate, what did we use really? So result is good physically for physics, but equation is too simple. So if we want to use the same idea, we need something that is more flexible or that goes at the core. So and I will call mode by mode phase mixing estimate what we really use behind that. That will be my first step to extend the method. It's not, you will see that it's not fully satisfying yet, but that's much better already. Call mode by mode phase mixing estimate, the following estimate in Fourier. Mode by mode means I'm doing that in Fourier, which of course you see already will limit a lot application range of the method because you can't always write Fourier if you're not dealing with the flat space and very simple characteristics. But anyway, we call mode by mode phase mixing estimate the estimate underlying the previous proof, both cases of the previous proof, which is actually we use that the solution for all modes satisfies something like that with a capital phi function it satisfies an estimate like that with a capital phi that goes to 0 capital phi that goes to 0 at infinity. Rate depends on initial regularity. Well, in that case, in V, for nonlinear problem, maybe it could be more complicated, but that's what we really used. And that's trivial when you solve the free transport equation. Let me just note that so that the statement is more general than the free transport equation. For the free transport equation, you see, it's just really saying that the solution at time t is actually the F initial Fourier at k eta plus kt. So that's just the decay in the second variable of the initial data. But as soon as you have something like that, you can deduce the two results I just gave. Now, previous points based on Fourier. So requires flat space plus characteristics, which is restrictive. How could we generalize that? So first, one generalization, which I've never been able to make much of it, but sorry. One generalization could be to use Fourier along curved characteristics, which might in some sense just be a pedantic name for doing harmonic analysis. And use stationary phase type arguments on oscillating integrals. Well, I suppose the reason, it might be the good thing to do sometime in cases like magnetically confined plasmas, I don't know. But the problem is that it's very Lagrangian, and most PD estimates have been built upon the idea of energy estimate, which is really the Eulerian viewpoint. Not in the spirit, sorry, of energy methods. It's also not clear how to get good global estimates from that. Your oscillating integrals might be a total mess. You might need to do surgery to understand them in some part of the domain and so on. So I think by far the best viewpoint, it is inspired from nonlinear waves in the late 80s. And the viewpoint of constructing vector fields that has invaded completely, for instance, GR. So the better viewpoint, again, will seem extremely simple in this basic case, but so to make it less trivial, because if it's too simple, you don't see really where it's going, I'm gonna give a sort of alternative way to get phase mixing. For this slightly more general transport equation, where I include again my B of V, and I will again assume that it's non-degenerate, and in fact this matrix is equivalent to identity. And I'm going to introduce the following vector field. So be careful, maybe I should state it more explicitly. G now will depend on V. It's a matrix. So I'm defining this vector field. So observe that it's okay. It's a gradient. So it's a vector field. Here it's the gradient x vector field, but you multiply it on the left by a matrix. So it still produces a vector field, and you have the scalar t. Then observe that if I define as well t for transport, my basic transport operator, then the commutator AT capital T gives exactly 0. So let's look at it. What remains in the commutator? So you search for the non-commuting part, obviously. So there is when dt hits t. Okay, in the way I put it, it comes with a minus because it's the other way around. So you have a minus GV grad x, and there is when grad v hits b, which is grad of b of v x. But they are the same things. They've been constructed so that we have this. So this is 0. So these two things are commuting. So I took a slightly more complicated example, but it's not that complicated. In fact, I gave you a transport equation that is more or less exactly this general form of an action angle UV. Sorry, it's the general form of the UV equation for an action angle reduced dynamical system. In practice, if you try to use that for a gravitational Vlasov-Poisson or Einstein-Vlasov or something like that, the difficulty will be to find the region in which you have action angle and to change things towards these variables. And of course, this is where everything will become complicated when you try to change variables. Hence, for all, let's say integers, and p just to emphasize what I'm doing, you don't really need all this p. You will have that the integral in xv of the vector field AT applied n times to ftxv. So be careful, this vector field, in fact, secretly has coefficients depending on v as well. To the p, that is not changing with time. So this is actually the same as what it is at time 0. Why is that so? Why it's immediate? Because simply transport of ATNF, F meaning f of txv, is equal to ATN T of F, and that is 0 because F solves the transport. So that is 0. Therefore, this is a solution to the transport equation itself. And we've seen that the solution to the transport equation conserves all the LP norm. So that's all. And now how could we use that? Well, it's not so hard. I mean, of course, this vector field, the part we are really interested in is this part, but we have to pay a price with this grad v. So it seems it's lost because we combine two vector fields. However, if we project along v, this part will disappear. That's more or less the idea of what follows. I did it with a test function, now I realize. Oh yeah, you need to. Yeah, okay. No, I thought it was too complicated. Okay, so how do we use this? Well, I'm gonna give you a sort of hand-waving arguments. Let's look at this term. I'm looking at t to the n of nx gradients of a velocity average of ftxv against a nice test function var phi, as I was doing in my previous proof. Well, first thing is that I'm going to include the t there, and I'm going to use that g is equivalent to identity to enter things into this. Okay, I should keep track of the parentheses like that. Okay. All good, but now it's not my vector field A, so I have to add, and this is the part where I will cheat a bit and skip details so that it fits onto a small screen, but try to do it. So here I'm gonna just cheat completely and say that this is this phi plus, of course, I add this by force, so it creates a lot of other terms, but the other terms will be lower order in x derivatives. The reason is that when you have only v derivatives hitting f, you put them back on the test function by integration by parts. All the v derivatives you can put back on phi by integration by parts. And the only highest order term is this one is already here. So the others are lower order. By this mechanism, and now you observe that this is just less than, how did I write it? Yeah, this is just less than that. So this is controlled by the initial term. Okay, so doing that argument properly, you take care of the lower order term, you reapply the same argument to the lower order term, and in a finite induction, you obtain finally a control of the this sort of terms is controlled, sorry, on the velocity average, of course, controlled if f initial smooth enough. And now you see that this is a phase mixing because you have the Tn. So you have a control and a decay on that term. Okay. So I would say that this I would suggest that this is the good viewpoint. I mean, it needs to be developed a lot. I mean, Renato Veloso is working actually on developing some aspects of that for matter orbiting a Kerr black hole, Schwarzschild black hole. But there's a lot to do because, I mean, in my case, it's very, very simple to identify the vector fields, but in general, you need to construct them, and it's not easy at all. But I would suggest it's a good viewpoint for gravitational Vlasov-Poisson or Einstein-Vlasov, and probably as well for tokamaks, I mean magnetically confined plasmas, where the structure is tokamak Vlasov-Poisson, when the structure is not clearly an unrealistic flat torus. Okay, so my last point, which will arrive at a first open problem, and then I will give a list of reference and other open problems, is that I want to make is connection between phase mixing, this, yeah, which one? Okay, let's be precise. Connection between mode by mode phase mixing estimates and the classical dispersion theory. Which will end up with, I believe, is a doable, maybe fun, small open problem. So consider, now let's go back to dispersive equations for a second. And the prototype of dispersive equation is obviously the Schrödinger equation. Okay, so let's write Schrödinger equation. So minus I dt psi equals Laplace psi, obviously, because I'm a mathematician, I've fixed h bar to 1, and h bar psi, the wave function is complex, and let's take x in Rd. Okay, this is the free Schrödinger equation. I'm not even putting a potential, there's nothing. And of course, you know that the free Schrödinger group, well, I could say semi-group, but it's really a group because, right, you can go both direction in time, is where xi is the Fourier of x, is dispersive. So what do we really mean dispersive here? At the physical level, it means we break the wave packets. So let me write down this, and then we'll prove a math equation. That means that we break the wave packet. So how do you see that? Well, either you've done that in math or you've done that in physics in undergrad. You just search for the dispersion relation between wave number and frequency for a given wave solution, for a plane wave solution. So what it means, you plug a solution that is a complex phase in t and in x, and you look at the relation between the frequencies. And that means you look at something like I don't know if it's plus or minus at 0 ID. I forgot. Something like that. And here, no, I'm not writing it well. Okay. Omega of xi should be xi square. I'm not writing the plane wave well, but that's the dispersive relation. Meaning the way the frequency in time should be related to the frequency in space like that. Okay, that's well known, and that's connected to the symbol of the PDE, and therefore gradient of omega of xi is twice xi, and that is what breaks the wave packets. So it means for nearby waves with different frequencies x's, you will have a big change of omega. Okay, so that means exactly that the waves with slightly different x's will have very different ways to evolve in time, and they will get torn apart and separated. Observe that it plays a similar role. Similar role to our grad B before. So that's where the non-degeneracy is. By comparison, for the wave, the standard wave equation, box U, it gives, of course, the dispersion relation, as you know, just modulus xi, which is not fully, but largely degenerated. So in that case, you have zero dispersion along the line. So there's no dispersion due to the amplitude varying of xi, only through the direction. So you lose dimensions of that dispersion if you want. Okay, so dispersive estimates are super useful, and there's a whole community built around that, as you know. Useful for at least the following two things that's well known. Stability of small perturbations around 0 or infinite mass solution. So the perturbation would disperse to infinity, that's the idea. Or, and that's of course the most beautiful case, subtle case where this linear, I should emphasize that the dispersion is a linear mechanism. The linear dispersion exactly balances the nonlinear effect to produce a persisting coherent structure, also known as a soliton. Okay, so that was just to say that these things are important, but I'm going a bit too slowly, so I'm not sure I'll have time to introduce all the open questions, but at least I will introduce this one. So now here is the funny thing. I have my Free-Schrödinger equation. Apply an old tool called the Wigner transform. So the Wigner transform, well, was introduced by Eugene Wigner, and it is Wigner transform of my wave function. So there's a constant here, which I think is that. And then you integrate W in RD. Then you have psi bar, the conjugate X plus W over 2. It's not my omega, right? I should call it V prime, maybe. Psi of X minus V prime over 2. And then you have EI V prime and dV prime. It's a sort of Fourier of the product psi bar psi on the anti-diagonal. Now it turns out that this Wigner transform it satisfies dt Wigner plus V. Well, it's not the name of the variable you would find typically in books, but I want it to look like my free transport equation. So this is again the free transport equation. So if my initial Wigner transform in smooth in V, which in fact, look at it, it's a Fourier transform. V is a sort of Fourier transform variable of the sort of matrix density built on psi, so a quadratic form built on psi on the anti-diagonal. So that corresponds to some localization of psi in your initial space variable. Then you have the phase mixing mode by mode estimate. Why? Because you just solve that in Fourier. And you will get some decay along eta plus KT, fast enough for our purpose. And then let's do a funny calculation. It turns out, and of course that's been known for a while, that the I forgot the name in quantum mechanics, the spatial probability, the probability of presence in space, so the square modulus of the wave function at Tx is nothing but the partial average along this V variable of the Wigner transform. So C at time t in L4 to the 4 is, shit. Sorry, I got a crash. I have to reshare. One second. Yes. Okay, so that's that could be written like that, right? I'm doing nothing here, but now I'm using that. I'm using Plancherel to say that this is the same as this square, this whole thing Fourier transformed. Let's call the Fourier variable xi instead of k. I called it k before, but it's not discrete. So, okay, let's call it xi. Before it was in x. And what this thing is just, this is just the integral in v, which is the mode 0 in the last variable, the Fourier v. So that is exactly integral in c of Wigner transform, Fourier transform, the Wigner transform, Fourier transformed in the two variables at xi 0 squared dxi. And now I solve my transport equation. Well, I'm using rather this mode by mode phase mixing estimates. Eta is 0, sorry, so I get that. And now you just change variable. You call xi prime being xi prime equal xi t. And you get exactly t minus d something finite. It's finite because these things decay fast. So summary, we have, of course, it's a long way to recover something well known, but the wave function in L4 would decay like t minus d over 4. But the interesting thing of this method is that to prove this, we go through a much more detailed and useful estimate, which is this. It's like unfolding a dispersion estimate into a more precise mode by mode estimate. So for instance, well, I'll mention this open problem and just two other ones, and I'll stop. So open problem, if I give you something that is sometimes called Gross-Pitaevsky, I'm going to try to write it properly. I think the sign is correct, but check it. And look at things just on the line. It's enough for the moment. So it's also sometimes goes nonlinear Schrödinger with non-trivial asymptotic conditions. So of course you see that you have many equilibriums here, many stationary solutions that corresponds to, for instance, being one on the whole line, or a complex phase just on the whole line, because then you kill that, and you just need to adjust that. Any simple plane wave satisfying the linear semigroup and canceling that, so having modulus 1 all the time will be a solution. And now the question is, of course, stability results when you perturb these solutions have been proved based on dispersive estimate. Is it possible to prove stability, nonlinear stability through the nonlinear stability would not be new, but what would be the interesting things through proving mode by mode phase mixing estimates on the Wigner transform, the Wigner, sometimes called the Wigner distribution of psi, but now on the nonlinear equation. There is a way to Wigner transform that as well. Okay, and since I don't have that much time, let me finish with other problems and then open to questions. Phase mixing have been used in plasma physics a lot for the so-called Landau damping, as you know. So there were results by Cagliotti, Maffei, and Huang and Velasquez of scattering, and the first nonlinear stability was our paper with Villani, and then another proof with Bedrosian Masmoudi. But it's still very limited what we can do in terms of geometry. So essentially, there's a whole world of things to do in order to deal with geometry. For instance, a tokamak is not a flat torus. We need to be able to understand how the damping happens with the confinement by magnetic field. The key point is to understand magnetic field. That's one important thing. At the linearized level, I really didn't have time to talk about the linearized problem, which goes back to Landau and Penrose. There are also problems remaining that are really important, for instance, related to Vlasov-Maxwell. In galactic dynamics, I think that it's again the same problem, but in some sense, it's even worse. What the situation actually is even worse. What we know is even less, let's put it this way, because really, my toy problem on which I've done all the calculations for you, which was this transport in a flat periodic box, at least bears some resemblance with a tokamak for a plasma, but it clearly bears zero resemblance with a galaxy. So what we know is even less. We need to understand the damping of a self-gravitating galaxy. I call self-gravitating, I should say maybe self-confined. Sorry, a galaxy confined by its own gravitational field. And for 2D fluid mechanics, the key breakthrough is due to Jacob and Nader Masmoudi in 2013. So, and the same problem, we have the same problem of geometry. So let me do I'm going to stop with the drawing, Jose, if that's okay. So for galactic dynamics, I don't think I need a drawing to convince you that proving the stability of the constant distribution of stars in a flat torus is not very realistic for a galaxy. For a plasma, I think you very well understand why it's a sort of approximation, but not very satisfying of a tokamak, where the plasma is confined by magnetic field. For 2D fluid, it's even worse in a way. The situation of the breakthrough in the paper of Bedrosian Masmoudi is the stability of an infinite an infinite quad flow in this sense. X will be periodized, and the second space variable is in R, and you have a quad flow like that. That's the linear quad flow, and you want to prove its nonlinear stability. And it uses phase mixing, where now Y plays the role of my velocity in the plasma physics and X of T, former X. So the framework is not realistic as well. However, this paper made a little step that is super interesting into not knowing in advance the geometry, because in some sense, when these things vary, when you vary along the quet flow, sorry, the limit will be something else that you don't know in advance. And that's a bit the equivalent of having a very small magnetic field for Vlasov. So they had to deal with a first step towards more general geometry. Now, what I mean by more general geometry would be, like I said, a plasma interacting with its magnetic field to produce a certain limit phase mixing structure, a galaxy producing a certain limit phase mixing structure, a fluid with boundaries or whatever, or how do you say, rotation, a fluid in 2D fluid in rotation, as you have in the Jupiter grid red spot. Or if you perturb, if you look at the matter perturbing a Schwarzschild or Kerr black hole, it will also change the geometry. And the key problem here is to construct a long time the phase mixing structure. What I call the phase mixing structure is the collection of characteristics, and the transport semigroup I've used during these 2 hours to show estimates for you. I've used the fact that we knew what it was, and for the paper on Vlasov-Poisson, we used with Cédric and then with Jacob and Nader, we used that we knew that asymptotically it would still be the free transport. We knew what was the asymptotic dynamic. We knew what the dynamic was scattering towards. In this case, they didn't know exactly, but they knew it would be very close to that. So they managed to deal with a very close to. For a 2D fluid in rotation, we have to deal with a movement, possible small movement of the center of rotation and lots of other things, and we don't know how to do this. So we need to find out how to construct the phase mixing structures and then to use the associated estimate. Maybe we don't need, maybe we can't know it in full details, but we would need at least to know the first finite dimensional parameters of it, the dominating ones. Okay, so I'm stopping here to give a bit of time for questions.
Thank you, Clément. Thank you. So please, questions. Just yeah, mute yourself, please, Michele.
I have maybe sort of naive question, but as far as I understood, all the proof of mixing sort of rely in the explicit formula you have for the transport. Are you aware of any proof that instead uses like weaker properties, just like, I don't know, the stretching of the actual, you know, the stretching that the flow is creating rather than actually looking at the explicit solution?
The stretching of what, sorry, you said?
Like we know, as you showed before, like we know that an area is stretched through a flow, but like this is of course true if you know the explicit solution, but in general, for example, it is enough to have a difference in velocities at the boundaries if you have any boundary. So like, are you aware of any proof of mixing that does not use the explicit solution, but weaker properties? Maybe you don't get rates, you get just the weak convergence or some sort of. Ah,
okay. Yeah, if you no, I couldn't quote a paper to answer your question. I nevertheless think that yes, you would certainly manage to get some weak convergence, but I'm not sure it would be usable to construct proof stability estimates in PD, nonlinear analysis. You know, you really need detailed estimates. Now, it's true I've done everything with very explicit characteristics. You don't need as much as I showed, in fact. It would be enough to construct, you know, to construct vector fields along. That's what I think this is by far the best approach. Here, it would be enough to construct a vector field that commutes with the evolution, and within which you can identify a part with a growth in time coefficient on the sort of action. This vector field is supposed to be differentiating according to the action variables, and this one according to the angle variable. I think it's a much more flexible vision of it. But you will need to know what I think cannot be avoided. You will need to know that you're in a trapped region of the phase space, that there's something orbiting, because this is really based on that, these phase mixing estimates. But I think there is hope that it could be done without so much explicit formulas indeed. And the good way to do it, I'm pretty sure, will be building good vector fields. By the way, I should have mentioned, sorry, to be fair to them, because I mean, it's a totally independent. I mean, I was discussing this sort of things a long time ago with Daniel Anquan, for instance, but there's a very nice recent note by Jonathan Luke and his PhD student, Sanchit Shadrus. I'm very sorry, Sanchit, if you hear that.
Everybody?
Yes, I'm not sure about the orthograph. I'll stop here. So, they have published a very nice note exactly along these lines and these ideas. And I think it's another sign that it could work. That it's a good way to go.
Okay, great. Thanks very much.
Any more questions?
Yeah, I have a question.
Yeah, go.
Thanks for your lecture. Does this construction of vector fields depend on Fourier type calculations as well, or is it completely independent?
No, not. I don't think it requires Fourier. You see here. In principle, I would not even need to have done Fourier before to identify that. It's purely algebraic. I mean, of course, you could argue that it's too simple, but nevertheless, this construction that I show here is about finding a commutator. It's not about, you don't need to write Fourier to find out that. It's using a particular commutating vector field with the flow.
It also in the more involved later calculations.
In the later what, sorry?
I mean, okay, so you explained this is kind of a method you can apply, but can you also go further? And when you go further, you have to use Fourier, or?
Further, like, you mean higher derivatives? In principle, you can do higher modes here as well. I'm not sure about if you. Yeah, I mean, I'm not against using Fourier in general, but I think maybe locally you would still do a bit of analysis or microlocal of stuff. But I think imagine a galaxy orbiting or matter orbiting around curved space-time. I don't think it's very realistic to think that you will do global estimates in Fourier for your whole system. It's much more realistic to build certain vector fields, I would suspect.
So this is really different from the Fourier method for the transport equation.
Well, okay. At that simple point, it is not so much. Okay, I think I got your question now. If B is just V, let me use another color. I took B of V to illustrate. Maybe I should have mentioned it. It's my fault. If you take B of V to be just V, then you get rid of that, right? It's just the identity. And then this vector field could have been expressed easily in Fourier. And of course, surprise, surprise, it's exactly the variable along which we establish the decay in the mode by mode estimate. So here, in that case, what I'm writing is just, of course, a weighted estimate. If I would write it with 2, I'm just writing a weighted estimate in Fourier with that thing. Okay, so that's not so surprising, but already the reason I added this B of V, look at that now. With the B of V, I'm not even sure that it will be that easy to do it in Fourier already. At least it's not obvious to me. Maybe there's a way to, you know, to use tricks, but because if you Fourier transform in V, that might be quite messy what you get. Whereas here I can use that if B of V is smooth and has this nice coercivity comparison with the identity, you know, I will recover nice estimates of that type. I will reconstruct my whole vector field, use that there is a conservation in time of that whole quantity, and I will one by one estimate the terms. So I can't claim for such a simple equation you couldn't do it in Fourier, but at least this calculation I've written is not immediately easy to write in Fourier, it seems to me, because of the dependency on V. The good vector field has coefficients depending on V, so it's a mess if you Fourier transform it.
Okay, so I think maybe we.
Oh, there's one.
Here, I know there is somebody else. Amélie.
Yeah. I just want to ask, could you give an intuition why this mixing gives some stability, or like, yeah, why does phase mixing in general gives some sort of stability for nonlinear PDE?
Oh, yeah. That's a good question. I'll just write one line. I mean, I obviously decided to focus these 2 hours lectures on the phase mixing estimate as well. There would be hours to talk about the nonlinear problem, but the reason is the following. For nonlinear problems, I should have mentioned it, of course, but I'm going to write 2 of them, and that will be enough to illustrate. Rho is the density of F. Because that's for Vlasov-Poisson. So that's the equation we studied with Cedric, and the one Jacob and Nader studied is this one. I'm writing here the Biot and Savart law. So be careful, these 2 equations are slightly different. Well, let me call it Z, because in my picture of a quad flow, sorry for that, Z would have been X and Y, okay? But it's a space variable actually. So the key point is that that term that annoys you, which is the 4th term, which is the electric field for a physicist, or the gravitational field, the gravitational force, sorry, for gravitational Vlasov-Poisson, is a -1 non-local operator, so a -1 derivative of the spatial density. And that quantity converges strongly. That's what I showed, you know, in my estimate.
Yeah.
Okay, so it won't be that simple in the nonlinear case, because actually, okay, I have to skip that. It would be more complicated, but nevertheless, the fact that there is a convergence, a very strong decay that you can make very fast if you have regularity of that thing, means that its gradient will go to 0 violently. Well, violently, it needs to go to 0 really fast in order to prevent destabilization of your plasma. And this is why we require such high regularity. For the Euler case, very interestingly, the Biot and Savart law is not as good as this. So again, I won't have time to do this, but remember that you have your 2 variables in the quad flow stability, you remember? And you do local averages in Y, and you recover some phase mixing estimate on the local averages in Y. Y plays the role of the velocity for Vlasov. And here now this is not depending on the local average in Y. This is mixing both variables. It's an annoying rotated -1 order operator in both X and Y. But it turns out that you can still recover rates of decay on the coordinates t-2, t-1. And this is optimal. It's called the OR mechanism, or it has other names.
Okay.
And I didn't have time to mention, this is why also the article is beautiful, because this is very critical, this decay, and they still managed to close global in time stability.
Okay,
But to summarize, the nonlinearity does depend on the local averages on which we prove the phase mixing estimates. This is why it's useful.
I see. Thank you.
Yeah, I think probably we don't have more time to go with questions unless we want to skip completely the break. So we went 20 minutes over time. So Augusto, you have a question, you can continue, but I would say that this is officially the break starts now, and we reconvene at in 15 minutes, at least that people can have 15 minutes. Okay?
Okay.
So Augusto, you can continue talking if you want.
Oh, thanks.
I don't expect
okay.
people to stay.
Okay.
Okay, yeah, no worries. Thanks for the talk. I was wondering, so you mentioned that the gradient of B has to be non-degenerate. So what happens if it's not? Like if it's like there's a point for which it's zero?
It's a very good point.
I think,
yeah, go ahead.
Can we do the same argument? Maybe, you know, like focusing on that point and having like less estimate, like
You're exactly right. What would happen typically is that, where is my slides? It's not easy to show it in this form. Let's go to Fourier, which is always simpler. I know I can't do it in Fourier. Sorry, no, I have to show it in this form. Yeah, what will happen is, of course, at this step, this inequality, you know, that's where the J is the gradient of B. Here I've used that it's fully coercive. And if there's a region of space where it's not, hopefully just a point, otherwise it will be, I mean, if there's a whole open set where it's not, you lose everything. I mean, if it will cancel somewhere. But if there's just one point, typically, and it's studied a lot by physicists, especially for plasma and 2D Euler situation, you expect to damage the decay rate. You damage it violently. Like you get a decay rate that will not improve with regularity anymore, but will be limited to the order of degeneracy, by the order of the degeneracy of your B locally. And this plays a huge role in many problems of plasma physics. 2D Euler as well. There is a paper by Freddy Boucher and a colleague about 12, 13 years ago about that for 2D Euler. So you can still do things, but it becomes much more complicated.
But it's possible to do these procedures in the case of degeneracy, like translate these.
Oh, that's a good question. No, I mean, I don't know if there is a case where it's been written rigorously. Maybe in the series of the series of paper by Nader and his co-authors on 2D and 3D fluid mechanics. I'm not so sure. No, the physics papers like this guy I mentioned, Freddy Boucher, the physics papers usually have the good ideas and intuition, but there's no real proof. They don't have these vector field techniques. So they do hand-waving arguments saying, well, what if I have a base like the Fourier basis, but I don't know what is the base? I mean, they are very unrigorous arguments. So they don't know how to prove it. They guess a decay rate by some Taylor expansion, saying, imagining they have a basis to decompose, or this sort of argument.
Okay, thanks.
So, but their prediction, I think, are correct. So you would expect something related to the order of degeneracy, some polynomial rate related to the order of degeneracy. So you need to take that into account if you want to close nonlinear stability. But I don't think it's available in the literature. If you have this problem in your research, you will have to reprove it from scratch.
Okay, thanks.
Okay, if there's
I have a question.
Michele says, yeah, there's a paper of Cotivelati. we use the vector field method for passive scalars equation, which is a sort of case of transport equation. Yeah. Sorry, there was someone else? Yeah, of course.
Yes, I have a question about. So you show that fast mixing is very powerful in the case of stable configuration. I mean initial configuration, but in plasma, I just take the case of plasma, and but most of the plasma when you have an initial condition which is not stable. And so I wonder how fast mixing behave in the case where your initial condition could generate instability and so coherent structure through the electrical field, for example.
Yeah, well, I don't have certainly an answer. I don't think there's anything published along that line, but in principle, for me, the way I think of phase mixing is as soon as you identify a geometry with these trapped trajectories and this non-degeneracy condition, that should help you stabilize whatever has emerged from the dynamics. But that's all. I'm not sure I can say more. You know, maybe it could help you to prove that the new structure emerging will be stable, but I'm not sure this would help you to know how the instability develops and so on. That's
no, but we know that instability at some point will saturate. But you have a kind of fighting between how could I say yes, phase mixing and trap particle in one sense, but in a self-consistent way. And I wonder how phase mixing can helps to identify your long-time behavior of your plasma. Because there is a kind of fight between two phenomena. I don't know if I explain well or not, but
yeah, you mean the moment plasma instability start developing, but this is already out of the range of the stability theorems we have.
okay.
I don't know. I mean, certainly instability mechanism. Well, maybe Pierre will speak afterwards and know a lot more than me about development of instability. They have their own techniques and their own methodology. I don't know if it can speak to this sort of stability estimate at the moment. So I don't know. Sorry, Nicolas. Okay, maybe if there's no more question, let me stop the sharing. Okay. Nothing more in the chat. Salut Pierre, ça va?
Salut Clément.